Yeah, I'm trying to be short. I'm Jianxiang Huang. I'm assistant professor at University of Hong Kong. I'm responsible for a small lab called Sustainable High Density Cities, and we work on modeling and simulation, and also urban new data analytics, focusing on the built environment human interactions. I'm going to report to you a fairly recent study that from the team of co-authors across 3 continents, and also our chair, Professor Huang also is among our collaborator, co-authors. That's fine, Professor Huang, you don't have to give me more time on this.
Okay.
And then,
oh, by the way, excuse me, Dr. Can you use the full screen? Full screen.
Oh, okay, full screen.
Yeah,
yeah well,
yeah,
I hope this is working.
Yeah. Okay, thank you. Now it's better.
Okay, good. Yeah. Yeah, quickly, we look at the COVID-19 as a close cousin of SARS, and then behavior. Well, in many ways, earlier version of behavior similarly, and then it draw our attention to high-density cities such as Hong Kong. I think Shanghai is also a high-density city, typical of that in Asia. And then there's some weird or Asia-specific phenomena happening. As Professor Wang Lan actually showed the research, actually density is a big factor. Really, we feel we feel that dearly, and also there's some strange, we call it the super spreading events in dense cities, and with tragic outcomes. And here are some examples documented in Hong Kong. So these are so people close neighbors, they live on different floor level in the same building or even neighboring buildings. And then actually they don't know each other. So, and they don't even share the elevator shaft, but there's suspected disease transmission that's starting from, I think the last year. So the research gap, as we put it, is that at that time, airborne transmission of COVID-19 is still debated, and then WHO guidelines have changed their mind multiple times. And then usually experts will point to that the outdoor environment is very safe. The sunlight can kill the virus airborne, and then we don't have to worry about that sort of outdoor transmission route. So, and then recent literature really is actually inconclusive about this sort of apartment to apartment transmission probability. So this is really the unknown in literature. And we suspect that many of these super spreading events in Hong Kong's high density neighborhoods are really through the pathway of outdoor transmission route from apartment to apartment. And then we're going to sort of use this curve to show the probability of infection versus the length of exposure. We can have really short exposure within seconds. For instance, the recent Delta variant transmission just take just a few seconds for people really to pass on that disease to another patient. Or we can take days of exposure with very low viral concentration. And that's also probable cause from infectious disease transmission perspective. So the way we do it is just use a computer model, because empirical forensic investigation is really, really difficult. And then that's medical experimentation is very limited. So computer models is our good tool. And then we use our own developed tool. We call it the ATTR, or airborne transmission by outdoor route. In this, we actually tested the model. We published a number of papers with good agreement between the validation, the measurement and predicted outcome. So the modeling originally was intended to simulate air pollution transmission and urban heat island, and then we find a good use. And then to really validate what we say with the computer model, we use this tracer smoke experiment that using Professor Hang Jian's outdoor field site. So actually we put in an artificial smoker the burning of smoking cake, that mimicking the virus-laden aerosols, and placed in an urban environment under various outdoor no wind or slight wind, moderate wind scenario. And then we measure the temperature, PM concentration, wind speed, and direction of those variables. And then that's actually showing very satisfactory agreement. I show you later about that chart. And then we use that case to study. This is one of the notorious sort of case in Hong Kong back in the SARS outbreak. I think many of us, if you have the memory, dates back 2003. This is a very tragic event. Hundreds of people infected, a lot of people die. I think that's really a kind of vicious cousin of COVID-19, as we put it. Biologists sometimes debate that SARS virus actually with COVID-19 virus, they're very close cousins, and sometimes they cannot be satisfactorily divided into different species. So if we look at that, the pattern of disease transmission, we actually obtained this the infection records. We know the primary patients living on the 15th floor of one block, one building, and then the other neighborhoods or households. They usually don't know each other, and people actually don't visit each other in high-rise buildings. And then that's transmitted in just within a matter of weeks. So most likely this is secondary infections from an epidemiology perspective. We also used another case of COVID-19 in public housing in Hong Kong. And this one is luckily or unfortunately with relatively small cases of infections. I think Hong Kong definitely learned the lesson after what happened in 2003, and then we only have 5 households actually who can be reasonably traced as secondary infection. Again, I think we think the outdoor transmission played a role between those apartments, and this is really the validation of our numerical model. Shows actually very good agreement. We can predict the rise, the wake effects, the buoyancy, the wind-driven flow, and then the plume of the virus-laden aerosols actually agree very well with the field observation. So we push our model to explain the almond garden transmission. We obtain that the pattern. I'm just go through quickly, and then we use a logit regression actually to see whether our predicted value concentration can explain the disease pattern. So this is sort of the dose response curve, and that really shows, with 95% confidence interval, that really shows that the higher exposure level, actually the higher risk of catching the disease. We use this Wells-Riley approach, the quanta emission. I'm going to skip that actually if you're not too familiar with that. Similarly, we use that model to predict the COVID-19 outbreak in Hong Kong in public housing, and then similarly we can also draw the exposed to response curve, and then the model actually can predict the risk of infection of all the surrounding neighbors, really based on the distance that you are from the index patient, and that's really sort of alarming sign for if you really close neighbors, you really leave downwind, or if you leave upper stairs from that that index patient, you really ran a higher risk of catching that disease, because the buoyancy flow or wind flow will carry the virus-laden aerosol to you. And then there's many what-if questions simulation can answer. What if there's no anthropogenic heat or buoyancy? And then the virus basically is going to stay down at a lower level, as our color showing. But if you have buoyancy flow, which means the warm air is going to rise up and it's going to carry the plumes with it. We compare this with another study, well-cited study by Professor Hugo Lee, and it seems like that our model through the outdoor can better explain the transmission in block E. I think Professor Hang Jing, you must know very well of this paper, this study. I'm going to skip this really fast. I think comes to the implication, the so what question. If we only have a single building or single high-rise building, let's say a super spreader residing in certain floor is going to exhaust a plume shaped like this. But if you have multiple buildings, and then that's going to change the way that the air circulates or the pollutant concentrates, there will be some spots that the pollutants can concentrate and stay highly concentrated. So that really just puts the exposure level highly uneven. There are lucky households and unlucky households. I think that's something, examples or lessons planners or designers should take. Or maybe another approach is to we apply positive pressure to ventilate high-rise buildings or centralize those the HVAC system in any way. It has a energy benefit. I think it also should have a health benefit. It really that's being pushed through. I'm going to wrap up. I think the study is limited in certain aspects. We only have 2 case studies, unlike Professor Wang Lan's presentation has so many data entries. And then we use simulation tools that's actually different from the measurement, although measurement is really difficult in the real situation. We conclude that the numerical tools are probably very useful to monitor or to diagnose those transmission cases, and they can retrospectively investigate what happened in the absence of measurement data. And that can be used as a design or planning tool. I think we have to develop this into a software, a Rhino plugin, so researchers or practitioners really can have a sort of assessment at the early stage. If you want to follow up with additional details, I'll be happy to send you that paper we published recently. Thank you very much. I end the slide.
Okay. Thank you, Dr. Huang. A very excellent presentation. And okay.